Okay, welcome to the optical communication course. We will see today what are the various types of fiber. There are a fiber based on what will be the uh, core and what will be the refractive index of a core of a fiber. Based on that, they have the types of fiber. So if that core is throughout that core, if refractive index is a constant, in that case, that particular fiber is called as a strip index fiber. And if the refractive index of a core is varying gradually, so that fiber is called as a gradient index fiber. So we'll see here in detail about that strip index fiber. In a strip index fiber, so the core is there. This one is about a core of fiber, and throughout that core, that refractive index is a constant here, throughout this given core. But in the case of cladding, there is a difference in the refractive index. Now I'm saying that this one is N1, so this becomes a N2 here. So throughout the core, that N1 is a constant. Okay, throughout this core, N1 is a constant, and but N2, if you can see the N2, that is a cladding refractive index. That N2 is slightly lower than the N1. Okay, N2 means that is a this one is about a cladding and a cladding refractive index. Okay, here we have say that core refractive index, that is N1, and a cladding refractive index and a cladding refractive index, it is a N2. So N1 is higher, okay, N1 is higher and N2 is a smaller as compared to the N1 here. So means we can say smaller or lower there, okay, we can say that smaller, will not use the word small in terms of height, okay, so it is nothing but a lower here. That refractive index, that is the lower here. So the profile, if you consider that for this step index fiber with respect to the radius, r is nothing but what we can say that core radius, or we can relate with a diameter also. In that case, we say that n1 is when we have that radius is less than a. So in that case, it is belongs to a core here. It will be n2 when we have that r2 is greater than or equal to a. So it is belongs to the cladding. So if you see that for a given fiber, so this is nothing but what we can say a radius. This one is nothing but the radius here. And for a core. Now this one is becomes a radius now. So total radius of a fiber is nothing but a r now. But only for this particular portion, if you see that this is nothing but a what we can say a. And if we throughout this a, throughout this core, so in which refractive index is n1 and that will be a constant here. So, but for a given particular strip index fiber, the core which is small or large, it is depending upon that what will be the modes. Okay, how many modes of a propagations are takes place through this. So in this case, we consider that there are we can say that a single mode fiber. There are the types of a fiber that we can say it is about a single mode fiber, and another we can say that is about a multi-mode fiber. Now, if you use the fiber for the single mode purpose, which fiber? That is strip index fiber. If you use a strip index fiber for the use of what a multimode one, so in that case, a diameter, we can say that a diameter that will be approximately that is 2 to 10 micrometer. But if you consider that a multimode fiber, in that case, the diameter of that core, okay, diameter that is we can say it is about a core diameter. In this case, core diameter is about a 50 micrometer. Because it is changes with what whether we are using this fiber as a single mode fiber or a multimode fiber. Now the strip index fiber can be used as a single mode fiber or a multimode fiber. So in a single mode fiber, only single mode, one mode is propagating through the fiber. But in the case of a multimode fiber, there are multiple modes are propagating through the fiber. So that's why you can say it is about a multimode fiber. Then if you consider the single mode fiber here, so what happened in the single mode fiber? So it has a low intermodal dispersion. Okay, it has that single mode fiber. Okay, we can consider that a single mode fiber has low intermodal dispersion. Now, what do you mean by this intermodal dispersion? Intermodal dispersion means what? When we are sending the signal, okay, from transmitter to the receiver, so in that case, a pulse broadening takes place. So that broadening of a pulse is a low here. Pulse broadening. We can say that broadening of a pulse, whatever the pulse transmitted is there, broadening of pulse is small here. But in the case of a multimode fiber, broadening of a pulse will be large there. So we'll see that at what about the multimode fiber here. So pulse broadening means what? For a given particular fiber, okay, we say this is about a core here, core of fiber, and this one is nothing but a cladding here. And we say that we have the device, it will transmit the signal now. Okay, we have this particular device, we say that it will transmit the signal. Now, for this particular case, when we are receiving the signal at the another end, light falls on the diode. This one is about a device. Here we can say that a signal is propagating. So means we can say that here we can say that it is about either LED or it can be also the laser source there. And here we can say that avalanche photodiode that is at a receiver. Pulse transmitted means light transmitted. Pulse transmitted means what? Here we have the conversion circuit. Means here we are sending the current pulse. We are sending the current pulse. So at the end, whichever the current pulse we are receiving, so it is likewise. Okay, so we can say that a current pulse is a changes here. Okay, so we can say that here, whatever the current pulse is transmitting, so it will be broadening here. So this is nothing but a broadening of a pulse. Broadening of a pulse, that is nothing but a dispersion. So we'll see that how that dispersion occurs. Okay, we'll see in detail how that dispersion occurs. Now we consider that if our fiber is a multimode fiber, okay, now we consider instead of a single mode fiber, we'll consider that a multimode fiber. So now what happens if it is a multimode fiber? Because as we say earlier, there is a pulse broadening takes place. What we can say that here is a pulse broadening takes place. Why the pulse broadening takes place? Because whichever the light is propagating through this, okay, so they are reflecting from the core, and there is a because signal transmitted from that this place to that place. Okay, so there is a variation in the velocity. of this particular signal because of some defects in the fiber or something. There may be a variation in the refractive index, or there may be bend and all. Okay, so that's why there is change in the velocity occur. So that's why you can say that is about it, that is called as a dispersion. But here it is only a single mode fiber, so this pulse broadening is small. But in the case of a multimode fiber, if you consider the multimode fiber, so in that case, multimode fiber, the core diameter is large as compared to the single mode fiber. So due to large core diameter here, we can consider that. So that rays are propagating through the fiber with a different frequencies, or you can say that different wavelength. So there are the various light rays are propagating through it. So they have the different, we can say that a different wavelength. So due to the different wavelength that signals are propagating through the fiber, so then what happen? There will be a dispersion occur. What happen here? So dispersion occur in this particular fiber because of which, okay, why dispersion occur? Because of the there are the different rays propagating through the fiber. They have the different velocities. So because of the different velocity, so difference in there they have the different group velocity because they have formed the groups with a single similar frequency component. They form the group, so they have the different groups. So they have the different group velocities. And while light is propagating through the fiber, so dispersion occur due to different in, or you can say that different group velocity. Okay, different group velocity there. Now because of that because of the different velocity, so that pulse broadening occur there. But if we consider that the fiber is to be used for in terms of a bandwidth for a single mode fiber, since we say that we can say that uh, that is what that data rate and particular bandwidth. If you consider that the bandwidth used here is a large, okay, but if you consider that with respect to the single mode fiber, so this multimode fiber is better at a lower bandwidth as compared to the single mode fiber. But why this multimode fiber is better for the lower bandwidth? Because of that, there are the different in the particular rays here because of the different rays there, and it requires a different that large numerical aperture for the given particular fiber. It requires a large numerical aperture, and because of that large numerical aperture, that core diameter is again large, and because of that large core diameter, so we can say that so they are easily coupling to the optical source with a different modes there. And then if you consider as compared to the single mode fiber, this one, that core diameter is small, and then due to the small core diameter, even the coupling is very difficult from the source to the fiber. But in the case of multiple fiber, so coupling, okay, if we couple the source here, so it will be easily coupled because of that core diameter is large. So we can use any source. So generally light emitting diode is used when we have that multimode fiber because the single mode LED cannot be used with a single mode fiber because it has that broad spectrum. Okay, emission spectrum of this diode is a broad here. So that's why for a broad spectrum, so multimode fiber is used. And then we can consider that as we say that diameter is a large, and we can say that that numerical aperture is large there. So because of this particular parameter, so number of guided modes, they are depending upon the whatever the diameter of this particular fiber, and number of modes are depending upon the diameter, as well as it is depending upon that what will be the wavelength of the signal that will be getting to the fiber there. So we can find out a total number of modes, or we can say that total number of guided modes. Okay, total number of modes propagating in a step index fiber that can be obtained using the what will be the mode volume. So we can say that ms is equal to what, v square by 2, and that value that will get that value because we have that a step index fiber is used for the various, we can see that for the various uh, propagating wavelength or propagating signal. Because of that, this can be used as a multimode fiber. For this, we can say that it has a difference in the core diameter there. Then, if you consider that the ideal fiber, okay, in that case, they have the difference in the core refractive index and their, we can say that they have the diameter variation in the diameter. So if you use a difference that the different core diameter there, so then coupling from the source to the fiber is difficult. But since here there is a large diameter of this core, so mode coupling will be easiest here. So likewise, if you consider that from the source to the fiber, it has a large acceptance angle. Similarly, for the mode coupling, it's very easy if we are using the multimode fiber. And then we say that power launching, or you can say that light launch inside this particular fiber is a very easy there because of that multimode fiber. Next fiber, we can say that a graded index fiber. Now in a graded index fiber, that core diameter, even if it is similar to the multimode fiber, but they have the variation in the refractive index at the core there. Means what, we can say that if you consider that this one is about our core of a fiber and this one is about a cladding of a fiber, so gradually that refractive index is a decreases here. Okay, gradually that refractive index is decreases. Now here it is highest from the center of this fiber core. If you move away toward the boundaries at a core and cladding, you can say that gradually that value is decreases. Now suppose, for example, I say that at the center it is supposed to be 10, okay, then 9, then 8, 7, 6, likewise. Means gradually that core refractor. We just take an example, okay, so that gradually it is decreases. But that there is a difference in what, a core refractive index and a cladding there. There is a difference in a core and cladding. So this, for a particular core refractive index, it should be higher as compared to the cladding here. But inside a core, that refractive index is gradually changes. So it doesn't have a constant refractive index as compared to the single mode fiber. In the case of a single mode fiber, throughout this core, throughout this core, it has a constant refractive index. But in the case of a graded index fiber, that refractive index is changes. Now in a graded index fiber, so that refractive index profile will tell you what will be the nature of that, we can say, refractive index of the particular core. So means we can say here that at this core it is highest one, and when you go away from this particular center of the core, it decreases. Means from this radial distance, if you go away from this core, so that we can say that it is decreases now. So n1 is vary. Okay, there is a variation in the value of a n1 here. So what is the refractive index profile with respect to the radius of the fiber there? So n of r, we can write n1 when we have that 1 minus price of delta divided by r by a, and that is to alpha, and that is to 1 by 2. When we have that r, that radius is less than a, then we can say it is about a core. But in the case of cladding, we say it will be n1 k minus twice of del raised to 1 by 2, and that will be is equal to n2. And that is when we have that r is greater than a. That is nothing but a cladding here. So that profile index, or we can say that a profile parameter, so that alpha, we can say it is the profile parameter for this refractive index. Alpha is a profile parameter here. Okay, alpha is a profile parameter. Now, if you use this graded index fiber as a step index fiber, okay, consider that for a step index fiber, generally consider that alpha is a infinite here. Okay, alpha is a infinite. So means there is a constant value of this refractive index. So that's why for a step index fiber we say that a constant core. So similarly we can say that that alpha is a infinite one. But here in the case of graded index fiber, that alpha value it changes. So alpha is equal to 2, means we can say that whatever the profile, that will be a parabolic profile. If alpha is equal to 1, then a refractive index profile, that becomes a triangular one. Okay, so we can say that it is varying now. Okay, so we can say that a triangular now. Means based on this value of alpha, that profile gets changes here. So I draw this profile, refractive index profile, for the different values of this alpha there. In that case, here we have this a radial distance we consider here. This one is about a radial distance, and then we have the core here, and this one is nothing but what we can say. It looks like a center. Now this one is a profile. It looks like a step index fiber. Now here it was n1, and this is the n2. Sorry, we have used n1 word here and n2 here. Okay, now n1. So abrupt change here, you can see that there is an abrupt change in the this particular boundary. This is a core. The refractive index is higher for, but if you draw a profile for the graded index fiber, so right now it is just like it looks like a step index fiber. So in that case, at this particular boundary, that alpha is equal to infinite. Why it is infinite? As we have mentioned that profile parameter, when it looks like a step index fiber, that alpha is really infinite. So similarly, alpha is a infinite here. Because of that infinite alpha here, so it looks like a step index fiber. But in the case of that alpha, if that alpha is a triangle in nature, okay, now this is nothing but we can say that alpha is equal to 1. Okay, this one if you can say that the property alpha is equal to 1. So then index profile will be a triangular in nature. So slowly, if you okay draw likewise, so then alpha equal to 2. Okay, so I'll use another here. So likewise, your alpha is changes. So index profile is depending upon that various values of that whatever the alphas we draw. Okay, so likewise, we have the variation in the values of alpha. So that is the last one. You can say that that is nothing but a alpha is equal to 10. Alpha is equal to 1 when it is a triangular one. Alpha is equal to 2. It is a parabolic one. So likewise, it is varying now. And for the given particular fiber, if you see, if you compare that like, step index fiber, and we can say that sorry, a gradient index fiber and a step index fiber. So then here for a step index fiber, alpha is equal to infinite here, and here this one is the variation in the refractive index inside this particular fiber. So alpha is equal to 1 means core profile gradually. This one is the center of a fiber. This one is about a center of. So, or I just draw here itself. Now this one is about a core, and now this one is the center. This one is the center. Gradually, that is profile is a decreases. Okay, that is gradual. That refractive index is a decreases, and here it is decrease. But it is throughout in this particular region. It is constant. So here we say n2 is a constant. Or if I draw here, I take a projection here. Okay, just like in that case, this one is nothing but the center of your. This one is about a core, and this one is nothing but a cladding here. Okay, this one is nothing but a core and a cladding. Now here, it is gradually changes. It is if you go from the center to this, it is decreases. That refractive index is decreases throughout this particular core here. Here at the center it is highest, center is higher, it is decreases. Now we can see that the both the fiber, that step index fiber and the gradient index fiber, you see internal structure, and we can relate that a refractive index profile for the given particular fiber. So we'll draw first. This one is about a core we say now, and this one is about your cladding. Sorry, and this is nothing but our fiber now. Now from this particular center, this is nothing but the axis of a fiber. Whenever we say that there is a variation in the uh, refractive index inside the core, so light launch inside the fiber in that case, so they will be reflected from the small particle portion. So likewise, they will be reflected at a given particle because there is a variation in the refractive index. There is a variation in the refractive. In another case here, okay, likewise, okay, it's not able to draw now. Draw by this way here. Now, why the different rays they are reflecting from the different bound? I supposed to be considered this one is a fiber end now. Okay, so in that case, we can see here there is a variation in the refractive. Likewise, because of that variation in the refractive index, whatever the light rays are propagating through it will be reflecting from the given particular boundary. Why? because a profile, if I say the profile of a fiber here, so it is varying now. Okay, it is varying now. So here throughout this is constant here, and it is changes with a, we can have profile here like this. Or I supposed to be I supposed to be consider again this particular portion here. So your profile will be looks like, okay, this one. I just supposed to be consider this one is about a profile of a, because there is a variation in the refractive index. So that's why they your signal or light is reflecting from a different places here. So that's why light is propagating through the fiber. It will be looks like this different this particular way here. We consider here that because they have the multimode transmission of a signal. This figure we can say that it is relating to this particular figure in a, this is for the multimode fiber because a multimode signal, multi signals are there with a different in a wavelength. Because of that difference in the refractive index profile, that transmission of this light or that light rays are propagating through the fiber, it will be looks like with a different or it will be reflected from the different boundaries. Okay, so that is about a example for this multimode fiber. But in the case of a step index fiber, if you compare with the step index fiber, what will happen in a step index fiber? So even if there is the rays, we can say that it will be reflecting from the boundaries of a core and cladding. Whichever the rays are propagating, they are reflecting from the boundaries of the core and cladding. So there is only the difference. Difference is simple here. So here with the different in the wavelength there, so they are reflecting at the different boundaries. And even if there is a difference in the wavelength, but the refractive index is a constant. Throughout the core refractive index is a constant. Means another ray suppose it will be reflecting likewise. Likewise, you can consider that. So don't get confused. We just say that we have the difference in the rays here. That's why we can say that your rays are propagating through it. Likewise. So, but it will be reflecting at the from this boundaries of a coherent cladding. But here, reflecting from where we have the changes in the refractive index occur from that particular place here. So, multimode signal can be propagating through the gradient index fiber. So, in that case, how many number of modes are propagating through the fiber? So, we can calculate using the equation there. And that is depending upon that what will be the index profile. We can calculate that for the gradient index fiber that modes are propagating is equal to alpha by 2 into what will be the refractive index of this particular fiber, what will be the wave number, and what will be the radius of the particular fiber into del here. Since we consider that a del is a small, so we can find out that V number is nothing but what? N1 Ka into twice of del bracket raised to 1 by 2. So if we solve the how many number of modes are propagating through this guide, in that case it will be alpha by alpha 2 raised to V square by 2 here. So if you consider that if your profile is a parabolic, so in that case alpha we can say that is about a parabolic. Okay, we can say that alpha profile if it is a parabolic in nature. So in that case for a parabolic alpha will be a 2. So in the case of if it is a parabolic in nature, for alpha is equal to 2, M will be what? It will be what? V square by 4 here. Okay, M will be what? V square by 4. But if you consider that if it is a triangular one, if it is a triangular, then alpha is equal to 1. So even if it is a triangular, it will be what? M is equal to V square by 4. Okay, that is about a sixth term. Okay, so now we can calculate that if it is a alpha is equal to 1, this will be 1 by 3. 3 into 2, that is a 6, that is V square by 6. So means there is a difference in the profile, whether it is a parabolic or it is a triangular. So what number of modes are different there. Number of modes achieved by this gradient fiber are a different. So we can consider whether it will be a single mode fiber or a multimode fiber. So then we consider here with the difference, or we can say that what are the advantages of a single mode fiber and what are the advantages of a multimode fiber, and then we can stop this discussion about a fiber here. Now we have said that here right now it is about a multimode fiber, but in the case if you consider that, for example, if you consider the single mode fiber, in that case we say that the diameter, okay, for the core it will be small for the single mode fiber. So because of that diameter is small, so we can say that there will be a small delay, okay, low delay. We can say that we have that dispersion, signal dispersion will be a low here, okay, or you can say that no dispersion or a small dispersion. We can say that is a small dispersion because that mode is propagating. It is a single mode. Because of that single mode of operation, only the fundamental mode can be exist through this particular fiber. Okay, means what? Only fundamental mode. Fundamental mode exists in a fiber. Now, what do you mean by this particular fundamental mode? That fundamental mode means what? LP01. Okay. So we have relate everything with respect to that team mode and all. So for a given particular fiber, we can relate with respect to that LP01 or LP11 likewise. So in the case of a LP11, so for how many number of modes are possible? So for LP11, in that case, VC is equal to 2.405. What do you mean by this values 2.405? That is about the for a given particular mode. Okay, for a given particular mode. So what will be the normalized frequency, or you can say that a normalized number. If it is a small diameter, because we say that the core of a fiber diameter is small, so approximately that VC is nothing but V. So we can say that V is nothing but approximately equal to 2.4. Okay, it is because instead of 2.405, we can consider it is about a 2.4. And this normalized frequency that can be adjusted by reducing the core diameter. Means what? If we reduce the core diameter, then V can be vary there. Or if we reduce that refractive index difference, and that refractive index difference is less than the del, if it is less than the 1%, so in that case, that normalized frequency can be changes there. Okay, normalized frequency factor this will be changes. This can be changes by reducing the core diameter, or this can be changes with the uh, difference of this refractive index is less than the 1%. So means, but even if we say that a small core, so then there are the drawbacks of the small core. What are the drawbacks of a small core? Due to the small core of a fiber, that launching light inside this particular fiber is a difficult. Okay, we can say that launching light, or we say that a power. Okay, launching light is a very difficult. Even if we join the two fiber, so we can say that a joint is a difficult. So two fiber when we are joining, so even if it is a difficult, so joint is difficult. And if you change the variation, we say that we require that is del is very small. So for what happen if we reduce the del? Okay, if we reduce the del, then it will be very difficult for the manufacturer, or we can say that, or producing the fiber or fabrication. Difficult for the fabrication. So means we can say that similarly we can say that even if there is advantages there, so then similarly we have the disadvantages of this single mode fiber. So we can find out what is the cutoff wavelength for this particular fiber there, single mode fiber. We say that bandwidth achieved by this single mode fiber, okay, in terms of bandwidth, so we can say that it is a okay, high bandwidth, or we can say that high bandwidth, low loss, because of that we can say that only single mode is propagating. So that's why it is about a low loss. And then quality of a signal, okay, quality of signal at a receiver, at a receiver will be a good quality because of there is no modal noise or modal noise here. So that's why we can say that a quality of a signal is increased there. Quality of signal at a receiver, that will be increased here because of that low loss there. And so we can consider that a transmission factors and all. We can calculate that a cutoff wavelength for this single mode fiber. That lambda c, that is a cutoff wavelength for the single mode fiber, it is about twice by a n1 divided by this Vc. We can consider that a cutoff wave number, okay, raised to 1 by 2 there. Or we can write a V here is equal to twice pi by lambda into a n1 twice of del raised to 1 by 2. So that we will we are getting everything with respect to what lambda. So we can calculate the even from this lambda. So lambda is equal to what? Twice pi by v from this equation. Okay, twice pi by v into a n1 twice of del raised to 1 by 2. By dividing lambda c by lambda means we can say that this is equation 1 and this is about equation 2. By dividing equation 1 by 2, so sorry lambda c by lambda. So we'll get that v by vc. Since we say that for a single mode fiber, vc is what? Approximately 2.405. So in that case, a lambda c will be a v into lambda by 2.405. So that what will be the operating wavelength of a given particular fiber, we can calculate here using this particular fiber. So generally this wavelength is nothing but what? 1.1 to 1.28 micrometer. Or we can say that a single mode fiber generally it is operating in a 1.3 micrometer of a wavelength. Okay, and So why 1.3? So to avoid modal noise, or reduces a dispersion there. Okay, this particular equation. Okay, so this one